One of the awesome guys I got to meet at the Idaho National Labs is Nicholas Woolstenhulme. He's a mechanical engineer working on the fuel for nuclear reactors. And his whole career has been working on the fuel for nuclear reactors. He gets to learn about all the fuels that are possible to make, test them out, figure out how to make them better, make them safer, make them more efficient. In this conversation, we dig into that. He brought me an amazing example of a 3D printed model of how fuel can be structured in modern reactors. I'm going to put a picture of that on the blog so you can see it. And I hope that you guys will learn something from this. I know these are deep nerd conversations, but we really have to have them in order to get to the bottom of what's possible from the people who are really in the trenches. And we're so lucky to have thousands of people in the trenches, engineers working on every aspect of making modern, safe nuclear reactors. We have all the talent that we need. We have all the people that we need. What we need to do is go build them. And I'm so excited to see that this country is finally getting our act together, finally turning around on sentiment around nuclear reactors.
I've never met anyone like it.
You could hack anybody's phone in a matter of minutes. Who is that guy? Who can do that?
Thomas is the most interesting man in the world.
He's one of my favorite people on the planet. Inventor.
Wicked smart.
The master of cutting corners.
If you had a dead body in your trunk, who would you call?
He would get arrested immediately in a lineup.
I stood in line to get his autograph.
You know, his mouth can barely keep up to his brain.
I don't actually know what Pablos does.
A hacker magician.
Man of the future. 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 Future.
My name is Nick Woolstenhulme. I work with the Nuclear Fuels and Materials Division. My thing is nuclear fuel, the thing that's in the core, that makes the heat. Been doing that my whole career.
Yeah.
A quick fun fact about me is that I am a third generation INL engineer.
Wow.
My dad still works here. My grandpa worked here, and
Yeah.
they all worked on nuclear fuels.
Wow, great.
So normally in Southeast Idaho, if you are third generation in your career, you're a potato farmer.
Okay.
But nuclear fuel is a family business for me. So
Wonderful. Amazing. My understanding, you can correct me if I have any of this wrong, so we dig up uranium out of the ground. Been decaying for zillions of years, millions of years. It's not fissionable. So we put it through this complicated enrichment process where we gasify the metal, try and get rid of the U-230, get as much of the U-235 as we can to make a fuel rod. And we stick that, and we're getting something like 7% of the energy that's in that uranium into the fuel rod. That's the more fissionable stuff. And then we take that fuel rod, which people think of as like the glowing green rods in The Simpsons, even though they're not glowing or green. You put it in the reactor, and then you get a couple of these fuel rods close to each other. So they create this fission reaction between them, and eventually they decay enough to where they don't do a reliable job of that. And then we get about something like 10% of the energy out of the fuel rod. And then we take it and put it in a swimming pool next to the reactor till kingdom come. So the end-to-end fuel cycle is like 0.7% efficient. And now we've got this, swimming pool full of super radioactive, dangerous stuff that scares people. And what part of that do I have wrong? Any part of that so far?
no, that sounds right.
Okay. So, all right. So just making sure, because, I don't want to have the wrong idea. So then the part you're working on is figuring out how we get the fuel, how we refine the fuel, how we make more of it, or how we handle it after it's been used. What the part of it that gets you going?
Yeah, mostly front end and in reactor stuff is what we work on. So we work on fabrication technologies for making more reliable fuel that can be taken to higher burnup, extract more energy from it.
Oh, interesting. And what might make that possible? So why would a fuel be able to get higher burnup?
A good example would be our current generation light water reactors. There is a lot of what I do is produce data for how those fuels would perform at very high burnup, high fission
Like leaving
densities.
the fuel rods in longer.
That's
basically.
correct. That's
okay.
right. Yeah.
Okay.
So I use Idaho National Labs test reactors to do a lot of to put specimens in reactors like the advanced
So
test
you
reactor.
can make a fuel rod manufactured maybe a little differently than what we used to do. And that might be something that you could leave in longer, burn longer, get more energy out of. Oh, that's super exciting. And what's the state of the art with that now? Is it Are we doing that in any production reactors, or are we still making fuel rods the old-fashioned way, or what's the?
That's a good question. Mostly it's state of the art and extending the data.
Yeah.
I should back up.
Yeah.
For current generation
Yeah.
reactors, there are some minor enhancements that are being added. People are looking at adding chromium coating to the cladding surface to improve its behavior, or doing different things with the uranium dioxide fuel pellets to make them a little denser. These are incremental changes. We get the sense that like the current generation reactors, they want another % here, another % there. They've got these reactors that have been running for decades, and they just always want one or a little bit more to keep them in business.
Yeah.
So we help with a lot of that, but that's probably only half of what we do. The stuff that I think is more exciting is really some of the more radical and innovative fuel design work.
Oh, okay. Cool. And what's an example of radical?
I'm prepared with what I think the coolest thing in the world is. It's a little toy for you to keep.
Oh, wow. I love it.
But-
Okay, sure. I see.
So you immediately recognize that's a 3D printed plastic prototype. You
but
and I
different
are both 3D printed nerds. So that's cool.
architecture here.
The pitch essentially is this. This is a small research project we're working on right now. Nuclear fuel, right now, you ask anybody who has basic knowledge of it, they'll say the word rod, right? They'll say it's a cylinder, right? Nuclear reactors, the cores are essentially just heat exchangers,
Yeah.
right? No surprise, the reactors we invented in the 1950s look like the heat exchangers of the 1950s.
Wow. I love that. Okay.
So here's a little more propaganda for you.
Okay,
In that
I'll take it.
in that upper right corner, you see a picture of an additively manufactured heat exchanger
Okay.
using this triply periodic lattice architecture. Other industries are doing this to achieve crazy good boosts in efficiency for their heat exchange. So we said, hey, let's put nuclear fuel in what for a heat exchanger would be the hot coolant side. Let's produce its heat. And then we'll have coolant go on the other side.
So this would be made of uranium, and instead of a fuel rod, you'd have this, what you could think of as like a, I don't know, perforated block. Or I'll put pictures online. But I guess you'd flow water through here.
Whatever coolant you choose. Yeah, water is a candidate.
Yeah, or I guess if you're making a new, so you wouldn't do this in an old reactor, you'd do this in a modern reactor.
So the whole point here is to massively uprate the power density of a reactor. We're talking like a factor of 3 to 5.
An existing reactor or a new one?
If you were to do that to an existing reactor, they probably don't
couldn't
have
handle
that sort of capacity.
Got
It's
it.
like putting a Corvette engine in
So
a
this is an
Pinto.
innovation you would use in a new type of reactor design. And so the coolant could be liquid sodium or something.
Sure.
And you would flow that through here, and you expect to get much higher heat transfer from this than old school heat exchanger.
That's correct, yep.
And is it 3x?
We know that the heat transfer coefficient from the experiments we performed is about 3 times greater.
Wow,
And there's other benefits too.
So if you didn't do any other innovations, but you could design the reactor core using this, you could get 3 times as much energy out.
Yeah.
Without doing anything else. Amazing. Okay, there's 3x. We'll take it. And then the idea, so this is actually an interesting one too, because you could do this with almost any type of modern reactor.
Right.
I apologize. I'm going to pause for 1 second. My daughter has tried to dial me 100 times, which she normally never does.
No problem.
She's supposed to be autonomous and know how to get by without me.
Supervisory control sometimes.
I have a 16-year-old. We understand. Yeah.
Yeah, I'm so sorry. It is normally, but it just keeps rattling my watch and my phone and everything. All right, I told her to wait. Hopefully she can handle that. I try to be the most negligent parent possible, and as a way of training her to not bug us. But yeah, I think she only wants money, which is easy to ignore. Okay, cool. All right, cool. So this is super exciting stuff. You guys are getting to really invent advancements for modern reactor designs. Can I put this online or?
Sure, yeah.
Okay, cool.
Yeah.
So I might do that in the show notes, because this is very interesting, and I want to read this and get to the bottom of it. But there's if you think about it, this is actually, I don't want to your invention, but it's embarrassingly simple in a sense.
Yeah.
Because you're just talking about like the heat exchanger in today's reactors, like the radiator from a Volkswagen Beetle or something. And we could do so much better and make them more efficient, even if we didn't make any other improvements. And obviously 100 other ideas, because we have 60 years of inventions like this that haven't been deployed. Knowing what you know about the fuel and the fuel cycle, if you had your choice of what reactor tech to use for a gigawatt scale reactor, what would you do? What's the best thing we could do right now?
I think it depends on when you want it.
Okay.
If you want it now, your only choice is going to be a pressurized water reactor.
Because why?
The technology is mature.
It's mature.
If you can wait just a little bit longer,
Yeah.
I love liquid metal cooled reactors.
Yeah.
I love liquid sodium.
Okay.
Makes a lot of sense for so many reasons.
Yeah. What's a good top 3 reasons?
Top 3 reasons: liquid sodium is excellent heat transfer behavior.
Yeah.
So it adds to this idea in a meaningful way.
And meaning using that instead of water, you get more heat out.
Correct.
Like, what's the factor there?
Oh, it's probably another factor of 2 or 3.
Yeah,
I think
wow,
it depends
amazing.
on the plant
Okay, got
design.
it.
But
Yeah.
you can have higher outlet temperatures with those types of coolants.
Yes.
So greater conversion efficiency, better process,
Yeah.
heat application. And I think the third thing is if you're using a coolant that is not water,
Yeah.
you can have a fast spectrum reactor. Traveling wave reactor, I know you're familiar with it. It's just one example of a reactor that has a much better optimized fuel cycle potential for fissile isotope utilization, right?
Yeah.
And if you can get into the fast spectrum, you can realize Enrico Fermi's dream, and you can do that. I think that's a big deal for the world.
Yeah, for sure. Do you think there's significant downsides to using liquid sodium?
Yeah, it's reactive. You have to be careful to.
I've seen what happens when I put a tiny bit of sodium in water.
Okay.
That's terrifying.
Yeah,
So as long as you can keep it separate from the water,
that's correct.
but we have to do that anyway.
That's right.
And what about things like, I don't know, thermal expansion and how much degradation you're going to get on the built reactor over time using liquid sodium? Is that better or?
Yeah, it's a lot better.
Oh,
It's my opinion anyway. The pressurized water reactor industry is, at least on the fuel side, has been working for decades to solve one problem:
Yeah.
corrosion, hydrothermal corrosion. They've done a good job with it, but it has taken decades to get it where it is. Corrosion is just one of the worst problems to
And
have.
does that go away with sodium or is it different?
You switch to liquid sodium,
Yeah.
and it goes away.
No corrosion.
Inert gas cooled reactors, same story. So it's a great problem to get rid of.
But you'd use liquid sodium on the inside of the reactor core and flow it through something like this or through your fuel. But then we also have another loop of liquid sodium on the outside of the reactor that would go out to
An energy conversion system.
for energy conversion. So there's those 2 loops. And what is the case where maybe you'd be a really good person to explain the difference between these different ideas for fuel? Like, what's a pebble bed reactor where the fuel is in these little balls instead of in rods? And like, what different? And then maybe you could also explain like HALEU and these other things. Like, since there's some confusion, I think, for lay people anyway, about what are these different fuels and why do we care and is there one obvious winner and that kind of.
Yeah, current generation fuel, really, cylinders are king right now.
Yeah.
Right?
How big are these cylinders?
For a light water reactor, they're centimeter. For a sodium fast reactor.
Diameter.
Yeah, diameter.
And then how long?
Oh, they're like, sorry to switch units on you here, but they're
Okay.
like 12 feet.
That's fine.
12 tall. They're big.
Yeah.
They're a little smaller, about half that length and half that diameter for a liquid metal cooled reactor.
Okay.
Now, you asked about pebble bed reactors. This is maybe one example of a reactor that does not use cylinders. They use spheres.
Okay.
So a popular concept is to use triso fuel. If you've heard of triso fuel, it's a coated composite architecture for fuel.
So what does that mean?
Little bits of uranium coated in lots of things to keep the fission products in.
So is it like a marble of uranium inside of a baseball of other stuff?
That's right, yeah.
Okay.
Except for the marble is very small, more like a BB.
A
but
BB.
Yeah.
Okay, it's a BB of uranium, and then what's the other stuff?
Usually graphite.
Okay.
And they
What's
call
the
them
point of that?
just to have something to hold it together and help scatter neutrons. They're usually thermal spectrum.
Okay.
They call it a pebble bed reactor. I've always thought it would be more like a softball bed reactor would be a better word. That's about how big they
They're
are.
a softball of it.
But they pile all these up in a core and cool it with usually an inert gas like helium, although there are some concepts that use molten salts.
They use helium as the coolant?
Yeah.
That seems dumb. Why?
Helium is not a great coolant for heat transfer purposes, but it has the convenient feature of being very inert and not having to worry about phase changes. And
But wouldn't argon at least be fine?
helium's the best of the inert gases for
Why?
heat transfer.
Oh.
It's just one of the properties of helium.
Right. Okay, well, it doesn't make sense to me, but fine. All right. So I'm opposed to anything that uses helium because we don't have very much left and
That is a
can't make
problem.
more yet.
Yeah.
And even in reactors, we can't make more yet. Okay, so we're not making pebble bed reactors in the U.S. though, as far as I know, right?
But there's a few
There's
under development.
under development. But China has deployed at least some or one, right?
Yes, I think that's correct.
Okay, so is there anything else besides rods and softballs that are being used?
Sometimes you see boutique forms like material test reactors, for example,
Yeah.
use like rectangular plates. They have really good heat transfer.
Oh, okay.
But they also do a lousy job at retaining fission gas because rectangles make bad pressure vessels. It's one of the reasons we love this fuel architecture.
This is amazing. What do you call this lattice again?
We're the government, so we came up with a good acronym.
Okay.
It's Intertwined Nuclear Fuel Lattice for Uprated Heat Exchange, or for short, INFLEX.
Great.
The beauty of this is you get continuously curved surfaces, so it can retain fission gas pressure and swelling like a rod would, but it also has heat transfer properties like plates would. So it's kind of the best of both worlds.
I presume one of the hard problems to solve in a situation like this is to make sure you don't end up with like eddy currents that get too hot.
Part of what we're studying.
Was this lattice engineered, or did you have some generative AI come up with it?
Presently, we have not started to use AI yet, and it's because the models that express its behavior, like at the fundamental level, still need to be developed.
Okay.
Which is why we're gathering the data that we're working on.
Yeah.
We generally find that CFD codes predict it well, but we do plan to unleash AI and topology optimization on this at some point.
You might want to just ping me afterwards, because I have a couple of modern CFD technologies I've seen that might be very useful for you.
Yeah.
I can connect you to those companies.
Here's a business card, by the way.
Okay, thank you. That's great. So with the fuel, once it comes back out of the reactor, I just think I know this is elementary for you, but I'm trying to dispel the myths and make sure people understand that this is not as scary as they imagine, because they really don't. Most people just don't even know what's going on. So if the fuel comes back out of the reactor, I got this 12-foot rod that's a centimeter in diameter. What happens to it then? Is it really dangerous? Is it really scary? Will I die if I touch it? What's going to happen with that fuel rod?
It is rather radioactive.
Yeah, sure.
Right. And it does generate its own heat, not nearly as much as it does when it's in the reactor, but it still generates a significant amount of heat.
Yeah, like how hot is it? Hot as an oven?
They always leave it underwater, so it never gets that hot. That's the point.
If I didn't put it underwater, it could get super hot.
Correct.
It could actually go super critical and melt down. It can't, but if two of them could.
Sure. Yeah. It's sitting there just making its own low-level heat, and if there's no water to remove the heat, or I'll say a cooling system of some sort, then it'll overheat. Yeah.
For how long? A million years?
No, it's just
120 years.
It's usually a couple of years. And then it can be removed and put into dry storage, which is all the nuclear fuel we have in this country. It eventually gets out of the pool, goes into a dry storage container, and that's where it sits to this day.
And how dangerous is the dry storage?
Not. If you've ever seen one of these things, they're very robust, concrete monstrosities. Yeah. And you can walk right up to them, and the radiation level is zero.
Yeah. Oh, wow. Wow. So we've really insulated against that.
Yeah.
Okay. So you don't lose sleep over the dry storage going wrong.
No.
You don't lose sleep over the rods in the swimming pool going wrong. Why not?
I'm an engineer, and I believe that good engineering can overcome these problems. I think that's a simple answer.
But do you trust, Russia and China to put their swimming pools together properly?
Yeah, that's a question I'm probably not expert enough to answer.
Feel free to opt out of anything. All right, fine. So it's manageable. What about skipped over this, but it'd be interesting to hear your perspective on the danger of the unenriched uranium, the stuff that we mined that hasn't been turned into fuel yet. How dangerous is that stuff?
It's pretty much a rock. It's barely radioactive.
Like I could have some on the table here and it wouldn't hurt us.
Sure.
Thanks. All right, great. So the dangerous part, what's the most dangerous part of nuclear reactors? If there was something to worry about and stay up at night, like we design them wrong, we build them wrong, airplanes crash into them, tsunamis knock them over. What's the thing that would be really bad for a reactor today?
I don't know that I've got a good answer for that
fine.
question.
That's great. And the reason that we can't have, so we've all watched Chernobyl on Netflix.
Yeah.
The reason that doesn't happen with our reactors is what? Like, why don't we worry about this having the same problem?
Yeah, I'm no expert in what happened at Chernobyl, except
fine.
that there were some irresponsible choices made in operating the reactor.
Okay, right. But once those irresponsible choices are made, and you get to the point where things are as bad as they can possibly get, and the thing is melting down, and what's that mean? It's all getting so hot, the whole reactor goes terribly wrong. Maybe something can explode and spit the nasty fuel rods out to where they could scare people. I'm sorry. Just trying to get to the worst case scenario is still in our heads. We have not experienced, we've never in this world experienced a civilian nuclear reactor going so wrong that it actually blew up a city or something.
Yeah.
Is that even possible?
I don't think so.
Yeah. Okay, cool. So I'll stop bugging you about that stuff. If you go back to just the innovations that are happening in this lab, do you feel like, what's holding us back or from taking these innovations, deploying them, and like really making a lot of progress with nuclear reactors? Is that out of your department too?
No, I think that's a fair question. You said something in your previous talk that hit me like a ton of bricks.
Okay.
It was to the effect of scaling up without doing basic arithmetic.
Yeah.
Right. And that's one of the things that worries me the most right now. I see that happening. I see it happening with research trends, things that sound new, sound like we should do them.
I feel like we did that with SMRs.
I agree. So
with the small modular reactors, like small just makes them sound friendly, but it's not really solving the problem because we need a lot of big reactors.
Yep. That's part of what we're trying to get at here is imagine a reactor that is as big as you can make it and still be able to produce it in a factory and ship it down the road.
Great.
Economies of scale.
Great.
Yet has the power output of today's gigawatt class.
Wow. You think
machines,
that's possible?
Right? That's the innovation we're working on here.
Amazing.
I think we can move that direction. So that's the inspiration.
It's so exciting to hear you say that. I see all the new stuff coming in the world, and to me, the most valuable thing, the most important thing would be to make big reactors in a factory the way we make Toyotas and ship them out around the world. That's so exciting.
And have them still be Toyotas rather than turning them into, I don't know, lawnmowers, right?
Yeah, or I call them Frank Gearys. These like very bespoke, very unique, one-of-a-kind creations like today's reactors. They don't take advantage of anything we've learned since Henry Ford, and it's disappointing. Wow, that's exciting to hear you guys are on that track. I would love to see that happen. Do you think there's things that you guys would like to have or that would help with the mission here or help advance the projects here? We came at it from the other side, trying to develop a nuclear reactor coming from the private sector. And I know that to get anywhere, that team partnered with you guys and other national labs to try and make some progress, and that's been great. But you think there's things that the private sector could be doing to help? What do you think of? We have a few of these reactor startups now. Do you guys look at them and just shake your head and think, oh my God, they don't know what they're doing? Or do you think that there's something that they should be doing or could be doing or something they can do that you can't do?
The answer to all those questions is yes.
Okay. Okay. Yeah, fair enough.
Depends.
Okay. Yeah. Okay.
Maybe I'll answer your question in two ways. What do we need?
Yeah.
And what could private industry be doing? We need a fast spectrum test reactor.
Oh, great.
So that we can study the way that nuclear fuel behaves under fission fast neutrons. That's something this nation does not currently have.
Okay.
And Russia is taking U.S. technology and doing it, right? We are getting left in the dust. That's a shame.
Yep.
The other way I'll answer your question is that what could industry be doing? Industry is already doing a lot to innovate on new reactor types. We're trying to come up with inventions like this fuel technology so that they can start designing their next generation of reactors around it. I also think that you can tell that this is a promising game changer idea for nuclear fuel, but it requires a significant change in the fabrication technology, right?
Yeah.
We can study fabrication technologies here and how they affect properties and performance.
Right.
We're the government. We're not going to go into factory scale production of commodities, right? We need private industry to get engaged in revolutionizing fuel manufacturing techniques.
Okay.
Some are doing that, but I see too little of that.
Yeah. So there's something you would want that I can't just dump uranium powder into a 3D printer and sinter it together. There's more to it than that.
That is one of the ways to make it, but it probably has inferior heat transfer properties.
Oh, okay. So we need more development. So what do you think you would want? 3D printers that could handle the uranium?
Yeah.
And
I would love to see a company working on a multi-material additive technology that has the right level of ventilation and inertness control to work with uranium-bearing material. So these technologies exist. They just all need to come together.
Okay. Yeah. No, let's make a wish list. So why is it multi-material?
Fuel plus cladding in this situation.
So this would be fuel with cladding.
Yeah, that little image in the bottom probably illustrates it best.
Great.
Right? So you have a fuel region, and then it's surrounded. The fuel region is a uranium-bearing material, and then the cladding region is something that stops that uranium material from being in contact with the coolant. Right?
Okay, got it. Got it. And because the uranium maybe could corrode or isn't as structural or something. Okay.
Yeah.
And so what's an example of a cladding material that's
In light water reactors today, they use zirconium alloys.
Okay.
A sodium-cooled fast reactor, they'll use typically iron-based alloys.
Oh, okay. Yeah, since
stainless
it's not
steels.
corroding anyway, they can use iron. They don't need Inconel or some exotic stuff. When you say uranium-bearing material, what's an example of that? Like you take the uranium and mix it with, I don't know, silicon or something just to hold it together? Or
Most of today's reactors are uranium dioxide, so it's a ceramic pellet. And then
Okay.
they put inside of a zircaloy tube. But there's also like sodium fast reactors, those that are to be built in this country by TerraPower, Oklo, and others. They're an alloy,
Okay.
uranium with zirconium. There's other
Okay.
suggested uranium
Yeah,
phases as well, but these
Thanks.
are the two most
So
prominent.
we want 3D printers that can print with those things and pretty high res because you would want the finish to be very high, very smooth for flow purposes. So we still need that. And so we need 3D printers that could do that.
Yeah.
All right, let's get on it, people. Okay, that's super helpful. So what else is happening around here that you're excited about or that you're working on that I didn't dig into here? I'm going to share this as really amazing stuff.
One of the things I'm most excited about that we're working on with industry is safety testing.
Okay.
Right? So we working with companies who are trying to license their reactors right now.
Yeah.
They have postulated 1 in a million events that will probably never happen, but
Yeah.
they still need to understand how
Okay.
nuclear fuel behaves if they do happen.
Sure.
This is like car crash testing
Yep.
for nuclear fuel. We do a lot of that testing here at Idaho,
Yeah.
using our transient reactor test facility. It's called TREAT.
Yeah.
And so that's exciting. We're doing a lot of work there.
Yeah. Have you gotten to make any mushroom clouds?
No, we don't make mushroom clouds. That's not our business.
What's the worst failure you guys have had so far?
Worst failure we've had so far. Can I say a failure to try on things that matter? Can I be a little more philosophic?
You haven't had any buildings blow up or
No.
anything so far?
Occasionally we'll have an experimental fuel specimen that does not behave as
Okay.
expected.
Yeah.
When we put these things into test reactors, we put them inside of containment loops, containment capsules,
Mm-hmm.
and everything is safely captured
Yeah,
and
cool.
nothing gets out. So we plan with that in mind, but
Yeah.
in a sense it's a failure because it's not what we hoped that fuel architecture would do.
Sure.
In another sense, it's a success because we've learned something about it and we've learned what direction to innovate next.
Have you guys been trying to develop any rad hard materials around here?
There are people working on
Yeah.
that. It's not really my field.
Yeah, fair enough. Cool. This is super exciting. I'm really thankful that you shared this, and I can't wait to show people. I
Fun
know
fact
on a
about
podcast
that-
they can't see it, but we'll put it online.
Fun fact about that geometry
Yeah.
is these regions, these intercontinuously curved lattices, they were invented by mathematicians
Yeah.
who were trying to find surrogates for structures they find in nature.
Oh.
So this is biomimicry in nuclear fuel. Right?
Wow.
So you find this shape in bone marrow, for example.
Oh.
Nature has had the ideal geometric architecture for nuclear fuel all along. It's additive manufacturing that allows engineers to access it.
Amazing. Yeah, you could never make this on a mill.
Yeah.
I don't think. Super cool. I'll let you go. I really appreciate the time.
Yep.
And I think people are going to love this. It's really great thing
Thank
to
you.
share. Yeah. And thanks a ton for that. I love to collect little examples of all the cool things that are coming. So appreciate it.
I see you already figured out it balances on its corner with
I've made a lot of these kinds of things for other applications as well.
Yeah.
This is, it's the foams and things that we can 3D print are incredible for structures. And
It's a really common shape for infill and 3D printing as well, low density infill that's
Yeah.
strong in all dimensions.
Yeah, I tried to do this actually as a way of making compressive materials for rockets when they land. We needed a way to absorb if the thing landed too hard to be able to absorb it. And so we tried using metal foams, then we tried using structured printed things like this as well. But that was 24 years ago. It's exciting what's possible with additive manufacturing. Well, cool. Thanks, man.
Yep, thank you.